We have another probability problem, also by me. This is problem number 5. Larry is playing with a toy car, so he wants to make a track for his toy car. Initially, he has a long straight track, but he decides to alter the track by choosing a point uniformly at random along the track to make a 90-degree right turn bend. He does this 3 times. One possible sequence of alterations is shown below. Now, in this case, the right turn bends in question would be this one, and this one. As you can see in this case, we would have 3 right turn bends starting from here. So Larry wants a safe track, in other words, one that does not self-intersect. What is the probability that he ends up with a safe track? Now really think about what is the condition for self-intersection. This basically just comes with a bit of experimentation. Let's move on to a new page to think about what possibilities there are. When will this sort of track with 3 bends self-intersect? Well, we know that every track will look like this, right? Starts upward, then turns right to face right, then down, then left. We can see the only possible way of self-intersection, well, we can see that these two are parallel, and these two are parallel. So what does that tell us? Well, then this and this will never intersect, right? The left and right. I guess the upward and downward facing lines will never intersect. And we can see that the only possible way we can intersect is this, right? So when does this happen, basically? One way to formulate this is by thinking about the lengths of these 4 regions. As we can see, there's a total of 4 regions adding up to some constant amount. Let's just call them A for this region here, B for this region, or this, yeah, and then C and then D. So we can see that we go up A and then down C, and then we go left to B, and then we go right D. So in this case, we want to say, okay, when does this happen? And this only happens when we have a situation where we don't go down as much as we go up. In other words, A is greater than C. And we also have B and D. Well, D has to be longer than B, otherwise we would have a situation like this, right? So you can see similarly, D has to be greater than B in order for D to sort of overshoot and hit the first segment of length A. So we just need these 2 conditions. So we can think about it like this, right? We can pick 4 numbers, of course uniformly at random, such that they sum to some constant amount. I guess it doesn't matter because it's all proportional. You know, maybe we can say like it adds up to 1, and we can think of them as proportions of the track. But we require, basically we're asking for the probability of, well, we want a safe track. So we can think about it as 1 minus the probability that it does self-intersect. Of course, A greater than C and D greater than B. This might be very difficult to consider at first, but maybe let's just think about one of these, right? Okay, how about A greater than C? What's the probability that if we pick 4 random numbers that add up to 1, right, picked uniformly, so they can be from 0 to 1, that A is greater than C? In this case, well, we have basically that probability should just be 1/2, right? Due to symmetry, there's no reason that A should be greater than C more than C is greater than A. So we can see that that probability is 1/2. One other way to think about it is that if we think, if we choose the 2 values and then assign one of these to A and the other one to C, then in exactly one of these cases, A is greater than C, and in the other case, C is greater than A. So that's just 1/2. Similarly, this is also 1/2, the probability that D is greater than B, also due to symmetry. So actually, if we think about it, there's actually really, there's no real correlation between these two. In fact, these 2 events, that A greater than C and D greater than B, are entirely independent, right? Because we can always swap A and C, and similarly, we can always swap B and D, right? There's no preference between the two variables. So actually, our probability here is just 1/2 times 1/2. Another cool way to think about it is if we choose the four possible, we choose the four lengths adding up to 1, and we sort of rearrange them in some, or we randomly assign A, B, and C, and D to these four values. What is the probability? Since indeed it's equivalent, right? If we pick the values of A, B, C, and D in order versus finding the values of A, B, and C, D in some order, and then assigning the labels A, B, and C, D, those are actually the same process. And they yield the same sort of distribution of results. So in this case, indeed, if you think about it, out of all possible permutations, exactly 6 of them work, right? In particular, you can list them out, right? And since relative order doesn't matter, or only relative magnitude matters, we can just think about them as like rearranging 1, 2, 3, 4. But basically, that's just the same thing, right? And again, these events of A greater than C and D greater than B are independent. So you should really just see that the answer is just 1 minus 1/2 times 1/2, or being 3/4, right? So that is our answer. And as a side sort of extra problem, I guess you can think about, for example, here, if you choose, for example, if you're throwing darts, this is a very interesting exercise in conditional probability. If you throw 3 darts at a dartboard, and you're given that the first throw came farther from the second throw, then what is the probability that the third throw was actually greater than the first throw? In other words, greater than both throws. So give that a think using this sort of idea of assigning labels after selecting the numbers. So have fun with that.